I'll be talking about topological defect networks, a framework for fractons. And this is work that I did in collaboration with a, with a gaggle of other postdocs, Dave Asen, Abhinav Prem, Kevin Slagle, and Dom Williamson, and references at the bottom of the page, and this is to appear in PhysRev research. So perhaps the historical starting point of this fracton story is with Haas code. And this is what is now known as a gapped fracton phase or a fracton topological phase. And it's a particular exactly solvable Hamiltonian, which I've written down. It has qubits on 2 qubits per site on a cubic lattice, but the details of it aren't terribly important. What Ha was aiming to do in his paper was to make a self-correcting quantum memory in 3 spatial dimensions. He didn't quite achieve that, but what he found instead was this very interesting model, which is now known as Haas code, and it has a complicated ground state degeneracy on the 3 torus, which is protected against local operation, against any local deformations of the Hamiltonian. And the degeneracy depends in a complicated way on the system size. Furthermore, the excitations, which are now known as fractons, are created by operators with support on a fractal, and no local operator can move an isolated fracton. This is a pretty unusual feature that is quite a bit more dramatic than something like topological order, in which excitations can't be created locally, but they can be moved with local operators. And this thing turned out to be a quote-unquote marginally self-correcting quantum memory. Can get into the details of that's not too important for the rest of my talk. But so this wound up after a few years. So that historically, this Haas paper was in 2011, and then it took about 5 or so years for the field to kind of open up. And at this point, what we have is a fracton quote-unquote topological phase as a general area of study in condensed matter now. And these are exotic phases of matter, which are gapped, and they have deconfined excitations in the sense that having widely separated excitations doesn't cost energy, but there are mobility restrictions. So no local operator can move these excitations in some of the dimensions of space. And these are not necessarily energetic constraints. These are really locality enforced constraints. So a fracton is a point-like excitation that's completely immobile. No local operator can move a fracton in isolation. Linons and planons are excitations which are point-like, which can only move in 1 or 2 spatial dimensions respectively. And these are really remarkable phases of matter. They have sub-extensive ground state degeneracy on topologically non-trivial manifolds and this degeneracy is stable to all local perturbations. So this isn't a symmetry protected state or anything like that. It's much closer in flavor to topological order. And these things are currently believed to only exist in 3+1 dimensions or higher. So these are a bunch of really brand new phases of matter, which have gained a lot of popularity and interest over the past 4 years or so. Now, there are a number of different types of fracton topological phases. So type 2 are perhaps the most sharply defined in the sense that they, oops, sorry, I thought I had a pointer. There we go. They are, the excitations in type 2 fracton phases are created by operators with fractal support, and all point-like excitations are completely immobile. They have a very complicated ground state degeneracy as a function of the system size, and Haas code is the best known example. Depending on your choice of definition of types, all other fracton models fall into the type 1 category. Some people use the term type 1 a little differently, and I'll get into that in just a second. so one possible use of the term type 1 is that membrane operators create fractons. So for example, you can apply operators on these orange dots on the left-hand side, and that will, or if you apply operator on those orange dots, you get excitations at the location of these blue cubes. And in general, fractons, these blue cubes may end up being fractons, and they tend to have mobile bound states. So if you put two fractons together, it might be able to move in a line or a plane or something like that. And these have a little bit of a simpler ground state degeneracy. Usually it's some constant to the power of the system size. And the best known example of this is the X-cube model, which I'm not going to get into I'm not going to explain in this talk, but it's kind of the paradigmatic model at this point. There's also a range of other models which are sometimes referred to as, some of them are referred to as type 1.5, which have a sort of a mixed character between type 2 and type 1. There's models where mobile excitations coexist with fractons, all sorts of different things of this flavor. But there's a big spectrum of fracton models, and most of these are currently understood purely from the context of exactly solvable lattice models. And so what we wanted to do is to have a framework which can deal with all of the fracton models. So current frameworks, some of them can deal with type 1 models and maybe type 2 models and abelian fractons. Some can only deal with type 1 abelian fractons. Some can only deal with type 1 abelian and non-abelian fractons, but can't deal with type 2. There's all of these different types. And to this state, at this point, hasn't previously been a framework which can actually encompass or describe all known fracton phases of matter. And so the goal of our project was to use tools from conventional topological order or topological quantum field theory to describe all different types of fracton models. And furthermore, we wanted to use algebraic data to describe those models instead of having to start from a microscopic lattice model for each different fracton phase. And the aim there is that we could distill it down to the algebraic data that describes a phase instead of saying, okay, well, this lattice model behaves in this particular way, but if we change the microscopic details, we don't really know if it's in the same model or in the same phase or anything like that. The aim of this is to use 3+1b topological order and to insert a bunch of topological defects, and I'll explain exactly what I mean by that, of different dimensions into it. This will stratify space, and I'll explain exactly what I mean by that. But inserting a big network of these defects will give us what we call a topological defect network. And we're going to choose these defects so that that the network as a whole is in the same phase as the desired model, in particular fracton models. And so in this talk, I'll use the X-cube model, the details of which aren't terribly important for our present purposes, but that's going to be what's guiding a particular microscopic model that we want to replicate from this construction will be guiding the construction. So let me just briefly say that defect networks are actually, in general, a very powerful tool. And invertible defect networks are a little bit of a special case of what we're considering, and they're known to be useful for constructing crystalline symmetry-protected topological phases. But one of the reasons that these are going to be interesting is that they relate fracton order to topological order without having to do any sort of strong coupling or driving a phase transition from some topologically ordered state into a fracton phase. And unlike previous constructions, we show in our paper that we can generate examples using the defect network construction that are in all of the known classes of fracton order. So that's kind of the big picture. Oh, and I also, as a result, because we can generate examples in all known classes, we conjecture that all fracton phases have a defect network realization. So that's kind of the big picture of the what we're trying to do. We have some construction which we want to use to describe fracton phases from algebraic data rather than from a lattice model perspective. So let me first talk a little bit about what defects in topological order look like. So let me start with an example. So suppose that we had the 3+1 dimensional toric code. This is roughly the same thing as Z2 gauge theory. So there's an electric charge and a magnetic flux loop as the excitations of this model. And if you braid the electric particle around the flux loop, you pick up a -1 phase. Now, what we're going to do is insert a plane in the middle of our box of, the middle of our box of topological order. So this box has the full topological order, and we're inserting a plane where the magnetic flux loop is condensed. And what I mean by that is that if I take a magnetic flux loop and I move it so that it's close to the defect, then all of the part of the loop that runs into the defect can disappear. And so by local operations. And so all that's left is a little magnetic flux arc here, and which ends on the defect. And the remarkable thing about this is that because an electric particle braids non-trivially with a magnetic flux loop, it turns out that the electric particle can't move through this defect. If I take the electric particle and move it into the defect, there's no local operator that can move it through the defect. And so it just kind of bounces off, or it can't do much. And so this is actually what's going to be useful in creating fractons, because if we think of the electric particle as a fracton, then it can move around. It can move around, but if it's stuck, inside any region that's bounded by these, bounded by these defects. So I'll explain that in a little more detail in just a minute. We're also another type of defect that you can put in topological order is supported on a line. And for example, you could have a line defect where if you take an electric particle and you move it close to the line, you can remove that electric particle without with a local operator. And so this defect condenses the electric excitation. So in general, for defects in topological order, what you choose is some surface of codimension greater than 0, and you condense some set of excitations there, which is choosing a set of boundary conditions at that defect. Now, maintaining the gap in the system is going to lead to some consistency conditions. And so we have to be careful. We can't do this arbitrarily. We have to choose a consistent set of condensations. But the fact that some particles and flux loops braid non-trivially with each other stops some excitations from passing through the defect. And this is going to be useful to make fractons. So let's see how this works. So imagine that we had a plane with these M condensed defects that I was talking about earlier on this orange plane. And let me add another plane and another plane in a different orientation. So I'm going to just keep adding a bunch of these planes throughout the entire space-time, the entire space, all of space. And I'm going to divide space up into little boxes using these planes. And when these planes intersect, something has to happen. That's a line of intersection. And so actually there's some additional freedom to choose a different defect at that intersection. And so if we do this in all 3 dimensions, what we do is we stratify space. So we break space up into a bunch of three-dimensional blocks, 3 strata, which are bounded by planes, 2 strata. And where these planes intersect is called a 1 strata, it's a line, and then many of these lines can intersect at a 0 strata.
I have a clarification.
Yes.
So these defects, do they have anything to do with lattice defects like dislocations, disclinations?
So that's a good question. So in general, that depends on the microscopic implementation. So right now I'm just specifying topological properties of these. So how the anions behave when they run into the defect. So if, for example, you had a bilayer system and you could imagine a defect which is a dislocation which switches you between the 2 layers. And that would be a particular example of one of these defects. But in general, they don't have to do, these defects don't have to be implemented by lattice defects per se. You're choosing some plane in the microscopic lattice where you're doing something different from the rest of the system, but it's not necessarily a dislocation or a disclination or something like that.
So a defect is basically like some sort of inhomogeneity which is restricted to a surface.
That's correct. It's restricted to a surface or a line or in general a point.
Okay.
Yeah.
I have a quick question.
Yes.
So in the 2D topological, like
Yes.
we can have the smooth boundary and rough
Yes.
boundary, which can condense E particle or M particle.
Yes.
So for the 3D, do we have a similar picture? Because I don't know the 3D boundary condition.
Yes, that's right. So for the 3D toric code, one of the 2 strata defects would condense the electric particles, and one would allow the magnetic flux loops to condense and end on them, and that's what I was showing here. So one of the defects condenses M, the other one condenses E, and then there's some more complicated defects that you can consider but yeah, I don't want to get into that. But there's a reasonable understanding at this point. We have a pretty good understanding at this point of the set of possible defects. There's one more where I think you wind up roughly you can think of it as binding semions to I think you bind semions to the ends of flux loops, but I would have to double check that.
Thank you.
Okay. So what does this stratification accomplish? Because it looks like we've just made a big lattice. And the point is that it gives us a separation of scales to work with. So we are going to be taking the microscopic length scale, A, to be much smaller than the distance between these defects, little l, which is much smaller than the whole system size, big L. And in this way, we can think of each of these cubes as being kind of in its own phase of matter, which we don't have to worry about any of the microscopic details within that, within each of these blocks. And so therefore, we only have to specify algebraic data rather than specifying an exact model. And that lets us bring to bear all sorts of tools from topological order. So I'm just about out of, looks like I'm just about out of time. So let me just briefly say that why we're going to choose the data that we do for some of these models. So one way to think about this is that space is divided up into a bunch of blocks. So these are called 3 strata. And in the X-cube model, what we're going to do is we're going to think of a single electric particle in a 3-stratum as being a fracton. So if we make it so that the electric particle can't move outside of the 3-stratum on its own, then this makes sense to think of this as a fracton, because there's some length scale over which we are not allowed to move this particle. It can move it inside the box, but it can't move out of the box if we make judicious choices. Now, it turns out that for type 2 models, for example, we have a construction for the Ha-B code, you actually want to choose a different topological order because Ha-B code has more types of fractons in it. So in that case, we might choose bilayer toric code so that there's more than one type of fracton inside. But let me just show you how this comes about. So suppose that we had two three strata that are next to each other and they intersect on a plane. So a bad choice of defect would condense a bound state of the electric charge on the left and the electric charge on the right. And the reason this is a bad choice for our present purposes is that we can create a pair of electric charges on the left side of the system and then move one of those charges to the defect. But then with a local operator, we could move that electric charge to the other side of the defect. And then it can just move freely into the next box over. So that doesn't restrict the mobility of our charges in any way. The thing that we wanted to be a fracton, this E, is able to move freely. So we don't want to make that choice. Instead, we choose the defect which condenses the magnetic flux loop because, as I said earlier, because this electric particle and flux loop braid non-trivially, it means that the electric particle is unable to move through this defect. And so if we cover every side of all of the three strata with this sort of defect, then these electric particles can never move outside their boxes. And this plausibly allows the electric particle to be a fracton. It's stuck inside its three stratum. So the last thing we have to do is make a particular choice of defect on the one strata. So this is where where four boxes intersect each other. And by choosing this, there is a particular choice where a bound state of 4 electric particles, one in each of the neighboring boxes, is condensed, but no fewer electric particles are condensed. And what this means is that single electric particles can't move through this defect, but we can create a set of 4 and widely separate them. And it turns out that and this is how you get a single electric particle inside a box by this particular choice of defect. And so what this does actually is it mimics a local operator in the X-cube model. And with this particular choice, you can show that you still aren't able to move a single electric particle outside of a cube. And so I just want to comment briefly, since I'm out of time, that you can build type 2 fracton models in a similar way. So we have a construction for Ha-B code, which is a type 2 model. And there's a correspondence between fairly complicated networks of string operators on the left side here, which create a set of widely separated particles with a fractal type, an operator with fractal support in Ha-B code in the lattice model. And so we can indeed build a wide range of fracton models using this construction. So some speculations on the applications of this defect picture. It might be nice to make nice wave function pictures for more fracton orders. Maybe use this to systematically classify fracton orders, in which case we actually really need to understand these defects fully and systematically, and I think that's not quite there yet. It might also let us suggest more field theoretic treatments for more general fracton theories, or to clarify the role of geometry, and also to study gapped boundaries of fracton orders. So let me just conclude there, and thank you for your attention.
All right. Okay, thank you, Danny, for your talk. We have time for maybe a quick question or two.
Yeah, Robert, can I ask a quick question, which is actually
sure.
3 questions, but they're closely related. So I'm going to ask all of them together because I think they're related. And they may not even be relevant. They may just reflect my complete ignorance, okay? So question 1 is that, can one do this theory without drawing any pictures at all? Like everything I do personally, I never have to draw a picture until I'm coming to the point of showing results, which may be numerical. but I do not need to draw any picture to do theory I do. So connected with that is the question that, is there a continuum limit for this theory? Meaning this discrete theory that you told us about, is there a continuum limit? Do you know whether a continuum limit exists? And the last part is that I don't quite understand the word field theory in this context. To me, field theory, you have to have a field, and field is a continuous function of space and time.
Yes.
So I'm missing something very major here, okay? I mean,
Sure.
Again, I'm sure it's my ignorance, but I would like to understand.
Yeah, okay. So let me go step by step. So in terms of drawing pictures, no, you don't have to draw pictures. So
when you work on it, when you are doing your
yes.
calculations with your friends,
yes.
you are not drawing these pictures to guide you along, or are you?
We are drawing. So we are drawing these pictures a lot. It makes life a lot easier to draw these pictures. But in principle, you can just write down operators. And
so I need an analogy. I need an analogy. It's like Schrödinger did most of the field theory. So Schrödinger was completely shocked when people started talking about Feynman diagram and Wick's theorem. He said, why do you need any of these things? You can just do the calculation. He never drew a picture because he could do the whole integral in his mind. So it's a bit like that, maybe. Drawing the pictures helps, right?
That's a pretty good analogy, because I can just write down so let me, rather than the defect network, which I'll get to the defect network itself in just a second, but if you look at one of these lattice models for these Fracton orders, you could just write down, okay, I have a cubic lattice with spins on the links, and the Hamiltonian is, a term which is a product of an X operator at site R times X operator at site R plus a half X minus a half Y, et cetera, and you just write down a bunch of Pauli operators, and it's fine. You just have a bunch of spatial indices that tell you exactly which links you're talking about. But once you draw the pictures, that actually shows you how it's useful for organizing that, and it lets you say, okay, well, from this picture, I can see that what I really want to be doing, is taking a product of Pauli operators on these particular links in order to, make the excitations that I want. So
other questions as continuum limit, and in what
yes.
sense is it a field theory? Yeah.
Right. So we don't in general know continuum limits for all of the for very many Fracton models. However,
but
for
do
some,
it exist or not? I'm asking even a more basic question. Is it known whether it even exists?
It's not known whether it exists for all Fracton models. However, we do have some Fracton models for which continuum field theories have been constructed. The X-cube model is an example, and in particular, there was a recent development of what's called a foliated Fracton theory, or sorry, a foliated field theory. Which there's like the idea is that the geometry of this defect net, it's closely connected to the defect network, because the geometry of the defect network is actually incorporated in basically a background gauge field in the theory. Called a foliation field, and so that does actually let you have some sort of.
Whose work is that?
So that's Kevin Slagle and a few others.
So your collaborators.
I'm sorry?
Some of your collaborators.
Yes, some of my collaborators. And separately, Natty Seiberg and company have also been looking at field theories at Fracton field theories.
And it's still a very active field, what you're saying.
Yes, this is a very active field, and I think, and Mason and I actually wrote down some field theories as well for certain Fracton models, which aren't connected to this defect network picture. I think those field theories are only approximate descriptions, and they miss some of the low energy physics, but they do capture some highly non-trivial low energy physics as well. So in that sense, there is some approximate continuum limit.
Okay, I think you have answered my question to my satisfaction. Okay, so it's not a trivial issue. Okay, so it's not like
very much not a trivial.
Not like I misunderstood everything. Okay.
Yeah. And
are there papers actually without any pictures in this field?
Yes, so there are some.
Danny Seiberg is not drawing pictures, right?
Yes, so in particular, the papers that are dealing with, usually the papers that are dealing with lattice models have quite a few pictures because it's just a lot easier to work with. But on the generalized gauge theory side of this field, things there are fewer pictures and a few papers without pictures.
Okay, thank you. I'm done. Yeah.
Okay. So I guess, huh? So yeah, I think we're a little bit over time. So I guess if anyone else has any questions, I guess you could always ask them during the discussion session later on, like round 4. So I guess we should now move on to the next speaker, who is Shaokai Jian. And his talk is dynamics of Renyi entropy in a coupled Brownian SYK model.
Okay, thanks for the introduction. I'm Shaokai Jian. I'm a postdoc at CMTC, and I obtained my PhD from Tsinghua University last year and also joined CMTC. My research interests include non-equilibrium dynamics in many-body systems, chaotic behaviors of quantum fields, and emergent phenomena in strongly correlated systems. And before I move to the main topic of today, I would like to make an advertisement about this chiral topological superconductivity in Josephson junction, because we know Majorana is the main topic, one of the main topic of CMTC. So here we consider the sandwich structure between superconductor, semiconductor, and superconductor. And these two superconductors have phase difference. And we also have a out-of-plane magnetic field. So the tuning parameter in this setup is magnetic field and phase difference. Then we find that in the phase diagram spanned by these two parameters, so N here is the BDG chain number. We can see the chiral topological superconductivity appears in a large portion of the phase diagram, and also in the non-trivial phase, we demonstrate the chiral Majorana edge states and the Majorana zero modes in the vortices. So if people are interested in this setup, we can discuss in the discussion section, or they can check out the paper as well. So let's move to today's topic. I'm going to talk about dynamics of Renyi entropy in coupled Brownian SYK models. And I would like first to acknowledge my collaborators, Brian Swingle. He should be in the audience as well. So I hope this paper can be posted in a few days. So let me first give some motivations. Hawking in 1970s considered quantum field theory in curved space-time. The black hole looks thermal from an asymptotic observer. So this is a state for an asymptotic observer. So here, B and B tilde are quantum outside and inside the horizon, and T is the temperature of the black hole. So these two quantum are entangled together. Black hole evaporates by this formula by emitting Hawking radiation that entangled with the interior of black hole. So let's look at the evolution of entropy of an evaporating black hole. We have entropy as function of time. Then we know the entanglement entropy between the black hole and the radiation increases because the Hawking radiation entangled the outside and the inside of the black hole. And we also know the thermal entropy of black hole will decrease because it evaporates. The energy is decreasing for the black hole. As we know, the thermal entropy always upper bounds the entanglement entropy. So there is a problem after the crossing point of these two lines. This problem is getting worse as time moves on. When black hole completely evaporates, what is left is a bunch of thermal radiation without anything to entangle with. So what is the right solution if unitarity is preserved? For a Hilbert space with two subsystems, we can regard one as black hole and the other as radiation. Consider pure pure high-random state in a full Hilbert space. The entanglement entropy between the two systems is given by this number, where I assume m is less than n. So m and n are the dimension of Hilbert space. And this result is obtained by Page. So you can see the entropy is bounded by the smaller Hilbert space dimension. So if we assume the black hole evaporation is unitary, and we also assume the black hole is chaotic enough so that its state is a high-random state, then this results. So the entanglement entropy between black hole and radiation will first increase because the Hawking radiation accumulate, and then decrease after the crossing point because it is bounded by the thermal entropy of black hole. So this is the well-known Page curve. And the transition time is called Page time here. Hawking radiation's entropy increases throughout the lifetime of black hole. So what is happening in Hawking's calculation? In the last year, a great breakthrough has been made. There's another saddle point that is overlooked by Hawking. And here is a list of pioneers contributing to this direction. In particular, Pennington, Amit, Inglehart, Maxfield are awarded New Horizon in Physics Prize because of this work. I mean, because of their contribution to this solution. So what is the new saddle point? It is called Replica wormhole. So here we consider a similar situation with two black holes. Instead of one black hole with the radiation, initially the two black holes are in product state, for example. Then the Hawking radiation from one black hole will be absorbed by the other. So the entanglement between the two grows forever. So here is the entanglement entropy between the two black holes. And this creates a problem when the entanglement entropy exceeds the thermal entropy of two black holes. So this is the information paradox in this setting. So let's now try to apply replica tree to calculate the entanglement entropy. And we make n copies of the system and calculate first Renyi entropy. So here's the definition of Renyi entropy, which we take nth power of the reduced density matrix of, say, black hole 1. So the reduced density matrix of black hole 1 is given by tracing out the black hole 2. So the boundary condition for this trace is simple. It basically connects the cat and the bra, while the boundary condition for black hole 1 is a cyclic twist, because we need to first multiply n copies of this reduced density matrix and then take the trace. So graphically, we can represent it like this. So for black hole 2, it is basically a circle. And for black hole 1, we have two twisted fields inserted. So gravitational path integral is then dominated by manifolds that fit the boundary condition. So let's look for saddles that satisfy the boundary condition. There is a naive saddle point, which is replica diagonal. So we basically fill in the geometry by connecting these two twist operators by a branch cut. And the space-time here, if it goes up, it enters another disk, but we can actually move these two disks, I mean, half disk to a full disk. Then the geometry is two disconnected disks. And this is, so the branch cut is nothing but the Einstein-Rosen bridge, and it will grow linearly forever. And it is responsible for this linear growth between two black holes. And this new saddle discovered by those people has the following form. So here we have example of Renyi 6 entropy. We have 6 boundaries. They are disconnected boundary, but the geometry can connect them. And this is the new geometry discovered by these people. After discover this geometry, we can calculate the Renyi entropy and then take n equals 1 limit. So this leads to the island rule. So taking this limit, the replica fixed point here in the middle will become conical singularity when you take this limit. And if you do extend it to a real time, you will find there are two islands outside the horizon. And this is exactly the new geometry that Hawking overlooked. So for evaporating black hole after the page time, a non-trivial gravitational configuration, the island emerges and leads to the saturation of entanglement entropy. This is the correct page curve. So in the beginning, we have Einstein-Rosen bridge, and in the late time, we have the islands. In this calculation, the gravitational path integral seems to play an important role, as it allows non-trivial configuration that connects different replicas. We are going to ask the following question: is the replica wormhole special as an outcome of gravitational path integral? What happens if we have unitary evolution of two black holes instead of black holes? What explains the page curve there? So let's introduce the Brownian SYK model. SYK model is a model consisting of n Majorana fermions with all-to-all interaction. And here's the Hamiltonian. Psi is Majorana fermion. J is a random variable drawn from a Gaussian distribution. And we have summation from 1 to n. So it is an all-to-all interaction. And it has quenched random interaction, meaning that the interaction is independent of time. And Brownian SYK model has Brownian type variable with variance given by this delta function in time. That means at every instant of time, the random variable is drawn from independent Gaussian distributions. And to mimic two radiating black holes, we consider two coupled Brownian SYK models. So we have two SYK models, and we turn on their coupling. Graphically, we have these two, and we have all-to-all interaction as well between these two SYKs, and we take this as Brownian variable as well. So this model is basically a circuit model. We can use operator dynamics to solve this model. We need a complete orthogonal operator basis by multiplying Majorana fermions from two systems. And this is a complete basis. And moreover, they are orthogonal because of these Majorana operators. So A and B are just lists of Majorana fermions from SYK 1 and 2 respectively. Then any operator can be expanded in this basis, and the expansion coefficient can be regarded as wave function because we know under unitary evolution, the amplitude of the wave function will not change. And also because of all-to-all interaction, the meaningful quantity is not any specific list A, but instead the length of the list A. This motivates us to define the probability distribution. So here, there is a summation of this wave function with fixed length in SYK 1 and 2 respectively. As the evolution of operator satisfy the Heisenberg equation, it will lead to evolution of the probability distribution, which is nothing but the master equation. The derivation is straightforward but tedious. Here I just schematically shown the result. So we have first order differential equation for this probability distribution, and we have outgoing flux as well as incoming flux. So we can get second Renyi entropy from the master equation. The whole point is that the density matrix is itself an operator, so its evolution will satisfy the master equation as well. So we can expand the density matrix as any other operator in this basis, and we have the boundary condition given by initial density matrix. Then the reduced density matrix is given by tracing out, say, SYK2. So this is traced over the basis, and we know all bases in the second in a system 2 are traceless because of the Majorana formulas, Majorana operators, except for the identity. So what is left is this is CA0. We need identity in the second subsystem. So gamma A here is the basis in subsystem 1. Then the second Renyi entropy is given by probability of finding density matrix in the basis of SYK1. That is, this is the definition of purity, or definition of second Renyi entropy. And we have square of the reduced density matrix. And if we expand this like that, and we have a trace between two bases, and this basically enforce A to be equal to B. So we have an amplitude of the wave function. And this summation is over all possible lists in SYK1. And we can convert this into the probability distribution of a fixed length. So PM0 is probability of having length M in SYK1 and 0 in SYK2. Then using this, we know the master equation will give the page curve. So we consider a product state between 1 and 2 initially, so there is no entanglement at the beginning. Because it is not an eigenstate of the full Hamiltonian, it will equilibrate under the time evolution. And here's the result from master equation. Indeed, the second Renyi entropy grows linearly at the beginning. That means coupled Brownian SYK can efficiently scramble the information between them. And it saturates at the thermal value. It is a constraint of unitary evolution. So we recover the page curve in 2 black holes. Now, what is behind the page curve? We need a path integral approach to review what is behind that. Recall the quantity we are interested in is the nth power of reduced density matrix. So we have actually 2 traces. One is for SYK2 and the other is for SYK1. For this
Shaokai,
SYK2.
Sorry, your screen froze for a little. Sorry about that. I think you're okay now.
Okay, thanks.
Sorry about that.
Okay, so we have basically 2 traces, and the trace over SYK1 is non-trivial because we need to first take nth power of this reduced density matrix and then take the trace. That means we have path integral of n replicas with twist operators inserted in subsystem 1. So for initial state, we again consider tensor product state. So the entanglement is 0 at the beginning. And graphically for system 2, the trace is a circle. And for system 1, there are 2 twist operators inserted. Then we make a complex continuation to real time, and this leads to a Keldysh contour. And in the Brownian case, we know the energy is not conserved, so there is no notion of temperature. So we can basically neglect this imaginary time evolution. And what is left is the Keldysh contour with 2 twist operators at the beginning and at the end. For simplicity, we consider second Renyi entropy. Then the effect of twist operators is to create such a configuration. We know we have 2 systems. A equals 1 and 2 are these 2 systems. And we also know we have 2 replicas. So we can take, say, a right and the bottom to be replica 1, and the top and the left to be replica 2. And the twist operator in system 1 basically create a coupling between 2 replicas. So that's, for simplicity, focus on system 1. And we use 1, 2, 3, 4 to label Keldysh contours of 2 replicas. So 1 and 2 are replicas for the first, 1 and 2 are Keldysh contour for the first replica. 3 and 4 chaotic contours for the second replica. Let's look at the saddle point solutions. The basic quantity in the path integral is the correlation function between Majorana fermions. So here we have correlation function between Majorana fermion at time t1 and t2. T1 and t2 locate at these contours if we consider second Renyi entropy, but we can actually consider more general case for arbitrary Renyi entropy. And this is the solution for saddle point equation. And here alpha and beta are replica labels. So this is a replica diagonal solution. And this matrix is standing for the chaotic space. And we also find another solution, which is replica wormhole-like solution. Here epsilon is proportional to permutation matrix, so it is no longer diagonal. The solution is general for any integer replica number. And let us look at n equals 2 for better illustration. So here is the plot of the solution. And we can see there is a non-zero correlation between 1 and 2. This is the correlation between the chaotic contour in the first replica. However, the correlation between the two replicas are 0. You can see there is no correlation between 1 and 2 and the 3 and 4. And here we also obtain this wormhole-like solution where we have correlation between 1 and 4, as well as 2 and 3. That means we have correlation between replicas. And this is very similar to the wormhole solution discovered in the gravitational path integral. So we can get page curve from these saddle point solutions. The path integral is given by saddle points at large n limit. And we know there are two saddle points. One is the diagonal saddle and the other is the wormhole saddle. And here is the contribution from these two saddles. And so F is a polynomial. So for contribution from wormhole solution, it is the prefactor is an exponentially small number. And at the long time limit, we can see there is a double exponential here. And this double exponential will approach 1 at long time limit. So the full contribution will lead to this exponentially small number. And for diagonal contribution, it is a decaying function of time. And at long time limit, it decays to 0. That means they must change dominance to the path integral as time increases. And let's define the page time to be when the contributions from two saddles are equal. So this is basically the definition of page time. And before the page time, this wormhole contribution is so small, so the diagonal contribution dominant. And this will lead to a linear increase of Renyi entropy. We have also checked this numerically, and this linear growing line is from the diagonal solution. However, after page time, we know the diagonal contribution will decay to 0. That means the wormhole will dominate. Yeah, this is the contribution from wormhole solution at long time. And that means the Renyi entropy is basically n log 2, which is nothing but the thermal entropy of Brownian SYK. And we also have this numerical check. And there is an interesting factor, the double exponential factor. It is from the twist operator. And this leads to the log n scrambling time. That means if you want to, so if the entropy want to approach order 1 before the thermal value, it will take log n time. If the entropy is, say, the thermal entropy minus an order 1 value, that means you need to take log n because you have exponential here. And this is also the shortest scrambling time you can have for many body system. Yeah, and here comes the conclusion. We show the purity of coupled Brownian SYK can be described by the master equation, and we obtain page curve from the master equation. We also formulate path integral representation and discover saddle points behind this page curve. The Replica wormhole-like saddle explains the saturation of Renyi entropy at late time. And Replica wormhole, as we can see, is not a special outcome of gravitational path integral. And with that, I would like to thank you for your attention.
All right, thank you, Shaokai, for your talk. We have time for maybe one quick question.
Oh, hey, Shaokai, this is Jay.
Yes.
So maybe just a issue about the Brownian SYK. I mean, so this doesn't have a defined temperature anymore at this point, right?
Yeah, there's no temperature. It is basically infinite temperature.
Infinite temperature. Isn't that a, I mean, I don't know very much about this story, so that's why, or about SYK in general. Isn't that an issue? I mean, I thought.
No, it is still a unitary evolution, even if you are in infinite temperature, and the saturation value is basically n log 2. So this log 2 is the entropy you have at infinite temperature.
But in the black hole problem, wasn't there a temperature? I thought
right.
Properties of the black hole, like event horizon and stuff, depended on temperature.
Yes, right. I mean, the black hole. So our question is to see any other non-gravitational system can have replica wormhole.
Okay.
And this circuit is even far away from this gravity.
I see.
Because if we don't have the Brownian, then we know SYK is dual to a gravity system. Once we have this Brownian case, it is even far away from.
Okay. Good. Thanks.
Could I ask a quick question? Can you speculate if there's any if like this sort of saddle point could show up in glassy physics, like a real glass or something like that, and if that would have any interesting physical consequences?
Right, that is a very good question. So here, we don't take the replica down to 0 or down to 1 to get entanglement entropy. So we are calculating the Renyi entropy. So basically, so maybe there will be some replica symmetry breaking scenario happening if we take n approaching 1 limit.
Thanks. Okay, yeah, I guess we'll have to move on now. So let's thank Shaokai again. Our third and final talk for today is by Seongjin Ahn, and it is entitled Fermi Surface Topology and Quasiparticle Properties in an Anisotropic Electron Gas. So take it away.
Okay, can you hear me?
Yes.
Okay, let me give you a brief introduction of myself at first. I got my whole education in Korea, and I got my PhD from Seoul National University under the supervision of Professor Hong Kim-in, who was also postdoc in CMTC about 10 years ago. And my research interest back in graduate school was to identify signatures of topological materials, like through optical properties or plasmons. And I moved to CMTC last year, and this is my second year postdoc in CMTC. I'm working with Professor Sankata Sarma. And my research interest at first, is first I'm studying many-body perturbation theory of the electron gas. This is something that is very classic textbook problem. So many people think that everything is already done for this. But after I discussed with Sankar, I just realized that there are so many things that have not been settled yet. There are many things to discuss still more. So I'm just working on this problem. On the other hand, I also working on the quantum computation. Recently, I worked with, in collaboration with the Professor Jason Kastner in UMBC. I worked on the charge noise problem in silicon quantum dot. So today's topic will be about the Fermi surface topology and quasiparticle properties in an anisotropic electron gas. So here we have an isotropic electron gas system. Here we have an isotropic electron gas with mass anisotropy. And the main purpose of this work is to study many-body perturbation theory of this kind of electron gas in the presence of mass anisotropy. This problem seems quite trivial, but I just realized that there are so many things that have not been done for this system. Especially, we're going to focus on the Fermi surface topology and many quasiparticle properties and the effect of this mass anisotropy on the Fermi surface topology and the quasiparticle properties. Okay, so let me first tell you about the motivation of the work on the Fermi surface topology. For the isotropic case, you don't need to really worry about the shape of the interacting Fermi surface. It's because Luthinger's theorem guarantees the interacting Fermi surface is the same as the bare Fermi surface because the volume enclosed by the Fermi surface is proportional to the particle density. So therefore, it should remain the same regardless of the strength of the interactions. But for the anisotropic case, there are many different shapes of the Fermi surface of the same area. That means that the interacting Fermi surface can deviate or be distorted from the bare Fermi surface. So here we have a bare Fermi surface as a dashed line. Here we also have the interacting Fermi surface. And what we noticed here is that many people, when they study an isotropic electron gas, they just conveniently approximate interacting Fermi surface as an ellipse, as you can see, as a solid line here. And what's very surprising is that people do not really justify anything on this approximation. They just use it without any justifications at all. So the natural question that arises from this is that the first one is that is the Fermi surface really an ellipse when the interaction is turned on? And if it's not, then how does the Fermi surface change as the interaction strength increases? And the second question is this elliptical approximation is valid in the first place? So these two are the questions that we want to address in our work. So in this work, we use the GW approximation, Z0W approximation. So this is a leading order GW theory. And this is just a diagram corresponds to the exchange diagram, but with the screened interactions. And here the screened interaction is obtained within the RPA approximation. As shown as the infinite sum of the bubbles. Well, originally, if you want to find the Fermi surface, that you're supposed to solve this kind of a Dyson's equations at the Fermi surface. And if you know the exact self-energy, then this gives the exact shape of the Fermi surface. But the problem here is that because we don't have any restrictions on the Fermi surface, you need to evaluate the self-energy at several k points. And those k points should also satisfy the Luthinger's theorem. At the same time, you should solve this self-consistently. Even within the leading order GW approximation, this calculation is never doable. And this is why people actually did not really do any work on the interacting Fermi surface of the anisotropic electron gas. And now we just want to tackle this problem by employing some method, by using some approximations described here. Now here we have a renormalized energy dispersion. It is typically written as the sum of non-interacting energy dispersion plus the real part of the self-energy. And just assume that the renormalized energy dispersion can be written in this form with the mass term having a momentum dependence. But this is not kind of a typical form of renormalized energy dispersion people use, because in an elliptical approximation, people just drop the momentum dependence in this effective mass. So these two are the real physical masses. But because we are talking about like the Fermi surface deviating from an ellipse, that basically means that this renormalized energy dispersion should not be an ideal elliptical, should not have an ideal elliptical form. That means that we should have some higher order terms right here. So these higher order terms, I just include those and observe these higher order terms in these effective mass terms. And this gives us several advantages. So assuming that these effective mass terms vary very slowly near the Fermi surface, this is valid for very small RS. And this is quite controlled approximation. So we can expand this renormalized energy dispersion around the Fermi surface using the Taylor expansion as shown here. And just using the very typical method for calculating the effective mass, we can just finally reach the formula for the momentum-dependent effective mass as shown and formula in the box below. Once you have momentum dependence of the effective mass, then it's quite easy to obtain the Fermi wave vectors. So here we have the Fermi wave vectors corresponding to interacting Fermi surface, so red KF. So we have black KF here. This is the length of the Fermi wave vector corresponding to interacting Fermi surface approximated as an ellipse. The ratio between these two, I just defined this as the eta symbol right here. And this eta has very important information. It tells us everything about the topology of the Fermi surface. Now, let's assume that eta is 1 for all values of theta. That means that the Fermi surface is an ideal ellipse. Let's assume that eta is larger than 1 for all values of theta. That means that it has a type 2 shape, which corresponds to this one. And if eta is smaller than 1, then that means that it looks like this. So this eta basically tells us, it does not really tell us everything about the Fermi surface, but at least it tells us about the topology of the Fermi surface and how much it deviates from an ideal ellipse. So here are the results of the eta as a function of theta, as a function of direction for several values of RS. And what I want to emphasize is there are two things I want to emphasize. The first thing is that there are only 2 types of Fermi surfaces allowed in this system, type 1 or type 2. We could not really find any other types of Fermi surfaces throughout these calculations. And the second thing is that as you increase the values of RS, as you increase the strength of the system, the Fermi surface topology changes from type 1 to type 2 or from type 2 to type 1. So this very interesting Fermi surface topological changes actually is quite interesting, but unfortunately it's very small. What I mean by small is that the deviation is very small. If you look at this number, and the deviation is like 0.3% or 0.1%, actually this is not experimentally verifiable. And this is what referees really didn't like about our work. But I just want to emphasize here is that this small degree of deviation from an ellipse somehow justifies why the elliptical approximation has been so much successful in describing experimental results. People use this approximation without no reasons, but we actually give a very good justifications of why this elliptical approximation has been successful. And another advantage is that using this approximation, we can calculate the quasiparticle properties very easily. For example, we can just drop the momentum dependence in the effective mass terms. So the renormalized energy dispersion would be written in the form right here without any momentum dependence in the effective masses. And this allows us to calculate the mass anisotropy versus interactions. So for example, here, as you increase the strength of the interactions, you see that both line mass and the heavy mass, they are enhanced by interactions. But the point here is that the many-body enhancement is much larger for the line mass than the heavy mass, which means that Coulomb interactions actually surpass the anisotropy. So if you're interested in this work, then you can just go to this reference to find more details. So having said about the elliptical approximations, its validity, and we can also obtain several quasiparticle properties of an anisotropic interacting system. But another approximation that people usually use is something that is called isotropic approximation. Especially when people talk about the correlation part of the self-energy or the system, they simply very conveniently replace this mass anisotropy with a single isotropic average defective mass. This simplifies the calculation, but people use this without any justifications at all. So this is the second approximation that we want to deal with. The first question is, when is this isotropic approximation is valid? And the second question is, what is the effect of the mass anisotropy on quasiparticle properties if the isotropic approximation fails? So these two are the questions that we want to address in the following slides. Firstly, let me show you the spectral function. The spectral function is basically the probability of an electron having momentum and with k and energy omega. So let's take a look at the non-interacting case. For the non-interacting case, we have three different states: the states on the light mass and the heavy mass, and in the isotropic energy band. And all these states have the same energy, and in the spectral function, they would appear as a sharp quasiparticle peak at the same position because they have the same energy. And this is the typical, what is typically happening in the non-interacting spectral function. When you turn on the interaction, however, you see that there is a broadening in the quasiparticle peak, and also there appears another peak which is called the plasma ion. It's a composite particle formed by the coupling between charged carrier and plasmas. And what's surprising here is that when you turn on the interactions, even though there is a manifest anisotropy in the system, but the broadening of the quasiparticle peak is well approximated by the isotropic self-energy, isotropic results, which means that in this regime, for the whole state, the isotropic approximation works quite well in describing the quasiparticle property. Yeah.
Oh, sorry, I thought you were cutting out there. Sorry.
Okay. So, and as you move upward to the Fermi surface, by definition, they should the quasiparticle peak appear at the Fermi energy with no broadening. And even for the electron-like case, far above from the Fermi surface, we see that even though there is a very clear anisotropy in plasma ion peak, but for the quasiparticle peak, the isotropic approximation works very well, and the spectral functions are quite isotropic in this case. What this means is that actually, in an RPS experiment, you want to somehow like observe the quasiparticle energy dispersions. Then you just need to calculate the isotropic self-energy in order to obtain the quasiparticle shift and the broadening of the quasiparticle peak, which is quite surprising. But as you increase the momentum more, as you move farther away from the Fermi surface, we finally see that the isotropic approximation fails, and we see that the separation between the quasiparticle peaks along different directions. And when you go upward, farther up from the Fermi surface, which is typically the region where the Fermi liquid theory fails. So because the Fermi liquid theory does not work at a large K far away from the Fermi surface, the quasiparticle peak is typically suppressed. But in this case, the heavy mass direction, the quasiparticle peak is strongly suppressed, but along the light mass direction, it's not as much suppressed as the heavy mass direction. So quasiparticle peak is anisotropically suppressed. Also, their position are quite different at these large values of K, which means that the isotropic approximation fails at this very large K, far away from the Fermi energy. Also, we evaluate the scattering rate as well using the on-zero approximation. And what you can notice here is that there is a very strong anisotropy at large energy, while near the Fermi surface, there is not a strong anisotropy. So to understand this, we need to understand the typical mechanisms of quasiparticle decay. The first decay mechanism is electron-hole pair excitations. If the quasiparticle is here, and the quasiparticle decays from this state to here, then this quasiparticle state releases momentum and energy, and this should be compensated. And here the compensation comes from the electron-hole excitations. So this type of quasiparticle decay, we call this the decay through the emission of electron-hole pair excitations. And there is another typical mechanisms of quasiparticle decay. So here we see that the quasiparticle decays from here to here. In this case, it emits the plasmas. So in this case, the momentum and energy conservation is done by the plasma emission. So now let's take a look at the scattering rate near the Fermi surface. And here, so Now let's take a look at this quasi-particle decay. So there are some allowed phase space for this decay because this quasi-particle cannot decay below the Fermi surface. So the allowed phase space for this quasi-particle decay is represented by the dashed line here. And the electron hole particle excitations, it also has a certain sort of phase space limitations. And this is represented by electron hole continuum here. And when these two phase spaces intersect, that means that the quasi-particle decay through electron hole pair excitations is available. And for this very small values of energy, the only mechanism available for particle decay is through the excitations of the electron hole pair. But at these very large values of energy, the story becomes quite different because in this case, this phase space for quasi-particle decay becomes larger. So it now covers plasma dispersion, which means that now the decay process through the emission of plasma emission is available for this value of energy. And this is why you can see this very sharp peak in the scattering rate. This occurs because of the additional decay channel through plasma emission. Now let's go back to the anisotropic case here. What you can see here is that the threshold energy of the plasma dispersion actually have very strong dependence on the direction of the injected electrons. And the reason why this occurs is because what the right-hand figure shows that the plasma dispersion in an anisotropic electron gas. We have some in-depth discussion on this anisotropic plasma dispersion, but I want to emphasize here is that the plasma dispersion is very highly anisotropic and they are not qualitatively the same. And even whatever scaling you use, you cannot really make these different plasma dispersions along different directions the same, which means that when the decay via plasma emission is dominant because of this anisotropic nature plasma dispersion, the scattering rate should be very anisotropic. On the other hand, when the decay via electron hole excitation is dominant, everything can be scaled. If you scale the electron hole continuum properly using the proper Fermi wave vectors, then you can just scale everything and there is no manifest anisotropy in the scattering rate near the Fermi surface. So, so far I have talked about, so in this work, we have studied the interacting Fermi surface in an anisotropic electron gas, and we found the interacting Fermi surface has only two qualitatively distinct shapes. And the degree of deviation is very small, so it justifies the elliptical approximations. And finally, we also showed that the unjustified neglect of the mass anisotropy sometimes can lead to an incorrect description of the quasi-particle properties in the presence of mass anisotropy. And thank you for your attention.
Thank you, Seongjin, for your talk. We still have plenty of time for questions.
Hi, Seongjin. I have a question. So in your model, it looks like, okay, in your theory, it looks like you consider the two decays with C2 rotational symmetry. So I'm just curious, have you thought about like other kind of rotational symmetry like a C4? And for example, you can imagine square lattice happy model, but you don't dop to the half fielding or very close to the bottom of band. You dop like somewhere in between the half fielding and the bottom of band, like a 1/4 fielding. And in that case, you also have this anisotropy Fermi surface. And I'm just curious, do you have any expectation on this case?
Well, I think as far as we consider the Coulomb interactions, well, my guess is that the anisotropy will be reduced regardless of what type of Hamiltonian you choose, regardless of the symmetry of the Hamiltonian. Once the interaction is involved, I think the anisotropy is reduced. The main reason, this is just my guess, but the main reason is that the Coulomb interaction itself is quite isotropic. So increasing RS, increasing the strength of the interaction basically means that the Coulomb interaction part dominates over the kinetic part. So my guess is that regardless of the the symmetry of the Hamiltonian. Once it is anisotropic, and once you turn on the interaction, then the anisotropy will be reduced and suppressed.
Okay, thank you.
So you didn't talk about RKKY interaction. Did you start looking at that? Does it go over straightforwardly with many body interactions? And if yes, I have some more questions.
We haven't thought about RKKY interactions here. Yeah, it's quite straightforward to calculate from our results, but we have never thought about it before. So,
But it would be the same formalism you use for non-interacting?
I'm pretty sure because you can easily, I mean, we already have this screened in the dielectric functions here. So we pretty much have everything to calculate the RKKY interactions, but we simply did not consider that in our work.
The only input for RKKY is this bubble. And the bubble is very hard to calculate, but Seongjin has already calculated the fully anisotropic bubble. In fact, not only fully anisotropic bubble without assuming even ellipticity. So calculating the RKKY interaction should be straightforward. I mean, it still would involve some calculation, but the main ingredient is already there.
Okay.
Work is done.
But with for an anisotropic Fermi surface like that, you have to be very careful which K vector you use.
Oh, of course. That's absolutely correct. Yes, yes.
Okay, it's not the obvious one.
No. Yes, absolutely.
Okay.
What I'm saying is, yeah, you're right.
Okay.
But the ingredient for that already exists in his calculation.
Okay, good.
This,
Thank you.
So does anyone else have any questions for Seongjin? So I guess if not, then let's thank all our speakers for today, and I guess now we begin our discussion session. So let me post the links to the two Gather Town chat rooms for everybody. And the password is CMTC RPA. Let me put that up. Okay, there you go. So so I guess let's head over there for further discussion then.
Thank you, Robert.
All right, you're welcome.